Hello students, today we'll discuss some important questions of electromagnetic induction. The first question for the day, the coefficient of mutual inductance of two circuits A and B is 3 millihenry and their respective resistances are 10 ohm and 4 ohm. How much current should change in 0.02 second in the circuit A so that the induced current in B should be 0.06 ampere? Students, please understand that the induced current is always in the secondary coil and they are asking us how much current should change in the primary coil so that we get this kind of current in the secondary or the output coil. Always remember, the current in the secondary coil is because of the EMF that is induced in the secondary coil. The EMF induced in the secondary coil is given by the formula coefficient of mutual inductance into delta I by delta T. We are not putting the minus sign because we are only interested in the magnitude. But however, this gives me the EMF. I don't want the EMF, I want the current. So for current, I is equal to ES upon resistance of the secondary coil. Now the resistance of the secondary coil is given over here as 4 ohm. Now if I substitute all the values that we have to find the change of current in the primary coil. Current in the secondary coil is given as 6 into 10 raised to minus 3, which is equal to coefficient of mutual inductance is 3 into 10 raised to minus 3 because it's millihenry, divided by resistance of the secondary coil is given as 4 ohm into delta IP is what we want to find out, divided by the time interval which is given as 0.02 second, that comes to 2 into 10 raised to minus 2. The 10 raised to minus 3 gets cancelled, 6 gets cancelled with 3, we have 2 into 4 into 2, that is 16 into 10 raised to minus 2. Hence the change of current in the primary coil is 0.16 ampere. Hence option D is our correct answer. The second question that we have is a solenoid of inductance 50 millihenry and resistance 10 ohm is connected to a battery of 6 volt. The time elapsed before the current acquires half of its steady state value will be. Now understand that in any coil which has inductance, as soon as the EMF increases, the current will not increase simultaneously because there is a backlash. The current which ultimately flows through the coil can be given as I naught, nothing but E upon R into exponential raised to R upon L into T. But over here they are asking us to find the time taken for the current to increase to half of its steady state. So now if I compare this is similar to the formula that we had in this radioactive decay, that is the number of atoms which are present at any instant is n naught into exponential raised to minus lambda t. The only difference is that this is the decay, whereas this is the increase of current which happens eventually. If we want T half, which over there it was 0.693 upon lambda, we could have done the same derivation over here, but we want the answer as quickly as possible. So this is 0.693 upon, instead of lambda we have R upon L over here, so this will be divided by R upon L. So now I want the half time. 0.693 is approximately 0.7. Coefficient of inductance over here is given as 50 millihenry, that's 50 into 10 raised to minus 3 divided by the resistance which is given 10 over here. So if I cancel, it's 5 into 0.7 is 3.5, 10 raised to minus 3 can be written as milli and seconds. So the answer is 3.5 milliseconds. Again option D is the correct answer over here. So the third, a conductor rod AB moves parallel to the x-axis in a uniform magnetic field pointing in the positive Z direction. The end A of the rod gets. Now over here we have to use a Fleming's right hand rule, which says that the thumb denotes the direction of the motion of the conductor, the index finger denotes the direction of the external magnetic field, then the second finger or the middle finger denotes the direction of flow of current. Now if the current is flowing from A to B, that means if the positive charge is flowing from A to B, then obviously the rod which was earlier neutral, if all the positive charge flows from A to B, then at end B the positive charges will be accumulated, and at the end A the rod will become negatively charged. Hence the correct option is option B. The fourth question, a very easy one, a straightforward question. It says that the current in a coil varies with respect to time t as I is equal to 3t square plus 2t. If the inductance of the coil be 10 millihenry, the value of induced EMF at t equal to 2 seconds. It's a very simple straightforward question. EMF that is induced is given by the formula coefficient of self-inductance into di by dt. If you differentiate this, you will be getting 60 plus 2. Now, this gives me the EMF. Multiply this with inductance, which is given over here as 10 millihenry. That comes to 10 raised to minus 2 seconds. So this is gonna be 10 raised to minus 2 into 6 2s are 12 plus 2, that's 14. That comes to 0.14 volt. Hence option A is the correct one. Question number 5. If circular coil of N1 is changed into a coil of N2 turns, what will be the ratio of self-inductance in both cases? Now, if you talk about the coefficient of self-inductance, if I compare this with the flux associated with the coil, we have flux is equal to L into I. The flux with respect to any coil is given by the formula NAB cos theta. When you change the coil, cos theta will not change now, but however the area, magnetic induction, both will change because area is given by the formula pi r square. Magnetic induction with respect to a circular coil is given by the formula mu naught into Ni upon 2r. Now the two things that will change over here. The first very easy, very obvious thing that everybody can see is that the number of turns will obviously change, because it's clearly given that a coil of N1 turns is changed into a coil of N2 turns. But what is not obvious and the hidden information is that when you change the same coil from a certain number of turns to another number of turns, the total length is going to remain the same. So if the total length, now the total length of any coil will be the number of turns multiplied by its circumference, that is 2 pi r. So initially if the number of turns was N1, the radius of the coil was R1. So if I change the number of turns, but obviously the radius is gonna change. So radius and number of turns are inversely proportional. So what I see over here is the flux associated with the coil, which is coefficient of self-inductance multiplied by current. We are talking about the coefficient of self-inductance will be N into N, that is N square into R square upon R, that will be R. Now over here N1 R1 is equal to N2 R2, that means the product NR is constant. So this into NR, this is also constant. This is proportional to, this is proportional to. Hence I can say the coefficient of self-inductance is proportional directly to the number of turns. Since it is directly proportional, hence L1 upon L2 will be equal to N1 upon N2, which means that option A is the correct answer. Now, again a very easy, straightforward question. You had similar question also in your boards. Question 6. A bicycle wheel of radius 0.5 meter has 32 spokes. It is rotating at a rate of 120 revolutions per minute, perpendicular to the horizontal component of the Earth's magnetic field BH. which is given as 4 into 10 raised to minus 5 Tesla. The EMF induced between the rim and the center of the wheel will be. Always remember, in such kind of questions, the number of spokes does not make a difference for EMF because all these spokes are parallel to each other. Okay, so they all have the center at the same point and their ends are connected. Okay, and they all perform same type of angular motion, hence does not make a difference what is the number of spokes. And in such question, the EMF induced between the center and the end, which is the center and the rim, is given by the formula half of B omega R square. Straightforward substitution, that's half into the magnetic induction is given as 4 into 10 raised to minus 5 omega. Over here this is 120 rpm, that comes to 2 rps. So this will be 2 into 3.14 into 2 rps into r square. Radius is half a meter. I'll write 0.5 as half. So this gets cancelled out. Okay, 4 gets cancelled out as 2. 2 into 3.14 comes out to be 6.28 into 10 raised to minus 5 volt, which is the very easy answer to this very easy question. So for question number 6, option A is the correct one. Question number 7. A closed coil consists of 500 turns on a rectangular frame of area 4 cm square and has a resistance of 5 ohm. The coil is kept with its plane perpendicular to the uniform magnetic field of 0.2 Weber per meter square. The amount of charge flowing through the coil, if it is turned over or rotated through 180 degrees, will be. Now students, please understand that when they are saying the amount of charge flowing, obviously the flow of charge means the current. But however, they are not asking us the rate of flow of charge, they are asking us the total charge that is flowing. So, if I want the current that is, by now we know that current is nothing but the induced EMF divided by resistance. The induced EMF in any coil is given by the formula d phi by dt, but this is for induced EMF. I want the current, so this is gonna be 1 upon R. But however, they are not asking us to find the current, they are asking us to find the total charge that is flowing. Current is a rate of flow of charge, hence I can say dq by dt is nothing but the current. This dq by dt is a current. Current is the EMF induced upon resistance. EMF induced is d phi by dt. So therefore, this dq by dt is equal to d phi by dt into 1 by R. Now if I equate this, I get dq is equal to d phi by R. But hello, I don't want dq, I want the total charge. Based on that, I can simply say that it is the total change of flux divided by R. Now the flux associated with any coil is given by the formula NAB cos theta. Over here the number of turns are not changing, the area of the coil is not changing, the magnetic induction or the strength of the magnetic field is not changing. What is changing is that the coil is rotated over. It is rotated through 180 degrees. So hence the change of flux will be NAB cos theta 1 minus cos theta 2 or cos theta 2 minus theta 1. Anyways, we are only interested in the magnitude over here. So if I substitute this formula, directly I'll be getting the charge. So number of turns is 500. Area of the coil is 4 into 10 raised to minus 4. Magnetic induction is 0.2 Weber per meter square. This will be cos 0 minus cos 180. So it is going to be 1 minus of minus 1, which will obviously be 2, divided by the resistance, which is 50 ohm, that is given over here. So very easy one. This gets cancelled out. This becomes 10 raised to minus 3. 4 into 0.2, that's 0.8 into 2, that is 1.6. So hence the charge will be 1.6 into 10 raised to minus 3 coulomb. This is the total charge that will be flowing through the coil. Hence the option is C. The next question, again a very easy one. It says that a coil of area A, which is given 0.5 meter square, is situated in a uniform magnetic field whose strength is 4 Weber per meter square and makes an angle of 60 degrees with respect to the magnetic field. Here please understand that the area vector which we needed is clearly given to be making an angle of 60 degrees. The value of magnetic flux through the area would be the formula that we have just seen in the last question. It is given by the formula N A B cos theta. Now it is a coil, so number of turns is 1. Area of the coil is given as 0.5. Strength of the magnetic field is given as 4 Weber per meter square, and cos 60 is but obvious, half. Half gets cancelled, it's 2 into 0.5 is 1, hence the answer is option B, that's 1 Weber.